Hello everyone. In the next 15 minutes or so, I would like to introduce you to our Synthetic Pebble Image Generator. This is a very simple synthetic pebble generator that generates spheres or circles and uses them as training labels for a SegmentAnything model. We are using this to validate our OrthoSAM approach with accuracy, precision, recall, and the intersection over union, I over U. I would like to point out that I am not claiming that this synthetic pebble generator is creating realistic pebbles. Instead, we are using this synthetic pebble generator to test the limits of OrthoSAM. So this pebble generator depends on a GPU code that generates shadows. So please make sure that you have your proper CUDA toolkit installed. This is something that you would need to do for your system, usually on a Windows system that is installed when you install the NVIDIA CUDA drivers. Just make sure that you have the same version running on a Linux system. So you can import the synthetic generator, and we have generated several versions of those, and I'm going to walk through these and point out why we created each of those versions. Again, we are not claiming that this is producing realistic pebbles, but it is a large data set that allows us to test the capabilities of segmentation algorithms. So the first test that we did is using black and white synthetic images, and the way that the generator works is that we set a minimum radius in pixels and a maximum radius, and then we define the image size. So this will be a 10,000 by 10,000 pixel image, so that will be a larger orthomosaic, and then the numbers of circles that we would like to place and how often we would like to try to place those circles. We don't allow any overlap of the circles. We don't use any random color because this is black and white what we have, but we are generating a digital elevation model, and that is just simply done by assuming that every pebble is a sphere, so that 2D circle projection is being projected into the z-axis as well. When we do this for the black and white image, we are generating a randomly placed size distribution. This size distribution is highly skewed because the larger pebbles will only be placed in random locations at some points, whereas the smaller pebbles can be placed much more often, and therefore you end up getting a highly skewed distribution. This is the associated mask data set, and this is the associated digital elevation model. We are not really using the digital elevation model for this black and white image, but we use that particularly data set to test for the lower detection limit of OrthoSAM, or the SegmentAnything model. And let's look at the manuscript. In the manuscript, we have the results figure and in the discussion figure 7 and 8, where we show the precision and recall as a function of diameter. And if we're using this black and white model, this is this black line, the precision is very, very high, but the recall is low, let's say below 30 pixels. This is 10 pixels, this is 20, this is 30 pixels. So below 30 pixels, the detection or the identification of pebbles or segments is low, meaning that if you have a data set where your pebbles are less than 30 pixels in diameter, you will have a low recall. So you should aim at 30 or maybe slightly more pixels in order to accurately detect them. So we used the black and white data set to detect this. We did not want to disturb it by shadows or color noise, and we clearly show that this is a strong signal. Interestingly is that this signal is more of a transient zone where the recall changes, which means that still some pebbles are being detected, but fewer. It's not an abrupt drop that at less than 30 diameters you're not detecting any pixel anymore. It's more or less a gradual decline. If we look at the intersection over union, we also clearly see our threshold. So this is 10 pixels. No, it's a logarithmic axis. This is 20 pixels, 30. So somewhere around 30 pixels, we are reaching an I over U above 0.9. So we have used this data set and we segmented it with OrthoSAM to perform these analysis. A little bit more realistic pebble data set can be generated by using colored pebbles. So we have done this for this data set here, where every pebble will have a separate color. Again, that's not really realistic. We are not having homogeneous pebbles, but we can add synthetic and random noise. And then we are getting a somewhat more realistic color distribution where you have the speckle noise. So this is a lower amount of speckle noise. If you would increase the speckle noise, you are going to mimic different mineral inclusions, for example. So this is an example of what can be done with this pebble generator. Probably the most realistic data set with this generator is created with shadows, and in order to calculate those shadows, you will need a GPU to cast the shadows and do it in a realistic amount of time for the 10,000 by 10,000 pixels. I'm not going into detail of the algorithm. You can look at the code if you are interested in this. Instead, I'm going to show you what this data set looks like. So this is using homogeneous colors, so there is no random noise added, but you see that the shadow casting here with inclination of 45 from the azimuth equals 0, so the sun is shining perfectly from the eastern direction. Note that we are using the mathematical definition of direction, which is 0 is along the x-axis, which would be the eastern, from the eastern direction in geographic sense. So we are casting those shadows, and we are particularly interested in seeing what happens when you have a shadow that kind of produces two segments, or when the shadow is being cast on the underlying pebbles, how does that affect the pebbles? And what we are describing in the manuscript is that the shadows, as long as a pebble is fully covered by the shadow, it will be perfectly detected. But if a shadow is intersecting a pebble, such as those pebbles here, which are intersected by this larger shadow, we expect to see difficult situation. The same that the largest pebbles that create a shadow themselves, that they are not being well segmented. So this synthetic data set we ran through our OrthoSAM detection, and I'm using a resampling factor of a half, or 0.5, in the initial data set, because 10,000 by 10,000 pixels would take quite a bit of time. So in order to speed up the processing and remain under the 30-minute limit, I have done a resampling of 1/2. And if we are scrolling down to the results of this, so these are the individual tiles that are being processed. I'm referring to the other detailed videos of the Ravi crop if you would like to hear the detailed explanation. And I'm coming up to the first results of the layer 0, so that half or 0.5 resampling. This is our RGB image. This is our segmented image, and that these are the segments masks. And you see that we are missing the large pebbles, the large circles, which is not surprisingly, because they are not covered by a single tile. So in order to cover those in order to capture those larger pebbles, we will need to resample even further. And in the second step, we are resampling by a factor of 1/4 or of 0.25. And doing that allows us to fit an entire pebble into a tile of 1024 by 1024 pixels. And then we are able to at least partly pick those up. So we are not able to pick up those large ones because they still don't fit into a segment, but we are able to pick up these ones. We are also seeing that we are introducing the first artifacts here. This is identified as a separate segment, that shadow area, which will mean for our purposes that this needs to be considered when you are looking at pebbles with significant shadows. So let's look at the merged version. So the merged version brings out these new pebbles. So these are the new segments that are added in the second iteration, and this is our final output. So if you would like to capture those large pebbles, you would need to do a higher resampling. For example, a factor 1/8 or 1/10 would be sufficient to capture those very large pebbles. So this is a very wide range distribution. We are picking up a lot of pebbles properly, but we are also seeing that there are some issues where the shadows occur, and that's something that we need to be aware of. Within the framework of our accuracy assessment, we are also providing code to assess the intersection over union for each of those pebbles. So for each circle, we have the true mask and we have the segmented masks. So we can look at the overlap of pixels and calculate the I/U. And the mean of all of the I/U pixels is for this example at 0.86. Because we are missing out some of the larger pebbles, it's not surprisingly that we don't have a better I/U. So this short video was just aimed at demonstrating the pebble generator. Many different things can be done with this, and I'm encouraging you to check out the associated Jupyter Lab, which is available on the GitHub repository. Thank you for listening.